Hello, welcome back everyone. Today we'll be going over section 5.5. This is a huge important topic in calculus, the fundamental theorem of calculus. So we'll jump right into the theorem. If f is continuous on closed interval AB, so we are including endpoints here, and cap f is any antiderivative of f of lowercase f, then the integral from point A to point B, so left endpoint, right endpoint, lower bound, upper bound, of lowercase of f of x dx is cap f of b minus cap f of a. So we'll start with one where I can convince you using just a geometric proof that the value we get with the calculus is indeed correct. So we'll start by checking out f of x is x plus 2. This is linear, continuous on negative infinity to infinity. And we're going to find the area from x is 3 to x is 6. So geometrically first, here we are in the xy plane. So here's our 3, here's our 6, and our line, we have y-intercept at 2 and a slope of 1. So just up 1 over 1, up 1, right 1, up 1, right 1, up 1, right 1, etc. So what we've done is drawn in a nice little trapezoid. You can look up the formula for a trapezoid. I find students are more apt to follow what's happening, since most of you know the area of a rectangle and area of a triangle to just break it into a rectangle and a triangle. So we'll start with the rectangle. The rectangle has a width of 3 units. From 3 to 6 is 3 units there. And there's my 9-month-old checking in, seeing how we're doing. Now our height here is simply f of 3. So f of 3 for this one is 5. So ordered pair is at 3, 5. So from 0 to 5, 5 units tall. So the rectangle has an area of 15 square units. As far as this height, we find f of 6. F of 6 is 8. So we have the ordered pair 6, 8 right here, but remember this would be 6, 5. So the triangle has a base of 3 units and a height of 3 units. So that has an area of 9/2 or 4.5 square units. So our total area should be 19.5 square units. Okay, now the calculus behind that. And the reason we want the calculus is, of course, our top function isn't always going to be a nice, pretty linear. It'll be curves at some point very soon. So antiderivative from 3 to 6, only now we have a definite integral as opposed to the indefinite integrals where we didn't have these endpoints. So integral from 3 to 6 of x plus 2 times dx. So cap f of x, they said, is any antiderivative. If we can pick any antiderivative, why not pick the one where c is worth 0? So antiderivative of of x is half x squared. Antiderivative of 2 is 2x. And then we draw a straight line. We're going to evaluate that from x is 3 to x is 6. Sometimes you'll just see the 3 and the 6 written here. So that's our f of b and our f of a. We chose c to be worth 0. No matter what we chose c to be worth, when we do that subtraction, it would have canceled anyway. So half of 6 squared plus 2 by 6 minus f of a. Half of 3 squared plus 2 by 3. So 36 halves is 18, 18 and 12. And we have our 9 halves plus 6. So we have 30. 9 halves is, remember, 4 and a half, 4 and a half, and 6 is 10 and a half. So there's our 19 and a half square units. So as far as linears, those we can either do geometrically or using calculus. Nonlinear, then we need the calculus. Okay, so our very next one, nonlinear example. So find the area under f of x is x squared minus 2x plus 5. It's implied that they mean and over the x-axis when we say area under a curve. So this time we'll go -3, 4 for our interval. So this one, our top would be a curve. We can't just use a nice, neat collection of rectangles and triangles. So we'll go antiderivative, lower bound downstairs, upper bound upstairs. And our curve, x squared minus 2x plus 5, close it up, multiply by dx. We pick any antiderivative, so we'll pick the one that has c of 0. So antiderivative of x squared, a third of x cubed. Antiderivative of negative 2x, x to the first becomes x to the second. Differentiate that, you'd have a 2 there. We have a 2, we want it to flip negative, so we'll just throw a minus sign out there. If you need to do the 2 and the 1/2, that's fine as well. And just clean it up on the next step, plus 5x. And we're evaluating from -3 to +4. So we have 4 cubed, 64 thirds, minus 16 plus 20. And then plug in our -3. So -27 thirds is a -9. 1, 2, 3 negatives makes it a negative. 3 squared is 9. And minus 15. So plug and chug on that. 58 and 1/3 square units. Okay, so this next one, I'll give you all one that turns out nice, neat, and pretty. See if you can find the area under the curve. I'll just put dot, 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 same directions. Find the area under the curve. Your curve is going to be f of x is 3 root x plus 1. on the interval 1, 9. They may also write it as from x equals 1 to x equals 9. That means still the same thing. Okay, give that a pause. Try it out, see if you can find the area, and we'll do it together. Welcome back. So our setup, antiderivative of 3x to the 1/2 plus 1 times dx, and our bounds, lower bound of 1, upper bound of 9. So x to the 1/2 is now x to the 3/2, just the power rule. And since we're doing an antiderivative, instead of subtracting 1, we're adding 1. Hang on to the 3 and multiply by the reciprocal there, so 2/3. Plus antiderivative of 1 is x, and we're evaluating that from 1 to 9. A little cleanup wouldn't hurt there. 2x to the 3/2 plus x, evaluated from 1 to 9. So the 9 to the 3/2 plus 9 minus 2 times 1 to 3/2 plus 1. Okay, so square root of 9 is 3. 3 cubed is 27. 27 by 2 is 54. So 54 plus 9 in our first one. 1 to any power is 1. So 63 minus 3, 60 square units. Nice, neat, pretty integer solution on that one. Now, occasionally we do run into substitution with definite integrals. I'm going to show you two options. I don't care which of the two options you use, whichever one you like. All right, so we'll start with integral from 1 to 5 of x squared over x cubed plus 5 times dx. That is a messy cube there. So that is an x cubed plus 5 in the denominator. So one option is to sort of leave the bounds a mystery and put the original x back in. Either way, though, our u here is x cubed plus 5, which means du is 3x squared times dx. We have a dx. We don't have a 3 there, so that means I'll multiply by 3 inside and 1/3 outside. That way they'll cancel out. I'm multiplying by 1 there. So if we're going to go back to the original x, we'll just leave the bounds a mystery. 1/3 integral from, we'll just call it a to b of 3x squared dx, that is our du. X cubed plus 5 at the bottom, that is our u. So then this is 1/3 natural log absolute value of u, evaluated from a to b. And then we put our original x variable back in there. So this would be 1/3 natural log of x cubed plus 5. And we're evaluating, instead of a to b, our original bound back, 1 to 5. So this would be 1/3 natural log of 5 cubed, 125. 125 plus 5, 130. Minus 1/3 natural log, 1 cubed is 1, 1 and 5 is 6. So that's one option, is to put the original x back in. Another option, same problem, same u substitution. U is still x cubed plus 5. Du is still 3x squared times dx. Another option, though, is to also translate the bounds from x over to u. Excuse me. So if I plug in the 1, 1 cubed is 1, 1 and 5 is 6, our lower bound becomes a 6. If x is equal to 5, substituting into our u substitution line, 5 cubed, 125, plus 5, 130. So integral 1/3 from, instead of 1 to 5, 6 to 130 of still du over u, which is still 1/3 of natural log absolute value of u, only now evaluating from 6 to 130, and I don't have to put the x back in. I can just do it with the u. So 1/3 natural log of 130 minus 1/3 natural log of 6. So same answer either way. Either plug the x back in and find it that way, or turn the x bounds into u bounds. You get the same answer. Like I said, I don't care which one you use on the quizzes and tests and such. All right, let's see, we'll do another one together. This time we'll do integral from 0 to 3 of x square root of 7 minus x times dx. So here I'll make my u 7 minus x, which means that du is -1 times dx. And if u is 7 minus x, I can also solve that for x. So then x is 7 minus u. So either our generic bounds of a to b, x turns into 7 minus u. 7 minus x turns into a u, and the radical is, of course, a 1/2 power. So du is opposite of dx. I didn't have a -1 inside, so I'll multiply by -1 inside and outside. That way I'm multiplying by something worth 1. Here's our du. So -1 integral from a to b of 7u to the half minus u to the 3/2 times du. Run out of room here. There we go. So we have -1 times, so u to the 1/2 is now u to the 3/2. So 7 gets multiplied by 2/3, so 14/3. And the sign there, u to the 3/2 is now u to the 5/2, which means I need a 2/5 there, evaluated from a to b. And then we can plug our original back in, or use the bounds on the u. This time I'll use the bounds on the u. So if x is 0, then u equals 7. If x is 3, then u is 4. So we have -14/3 u to the 3/2 plus 2/5 u to the 5/2, evaluated from our a used to be a 0, now it's a 7. Our b used to be a 3, now it's a 4. So -14/3 times 4 to the 3/2 power. Square root of 4 is 2. 2 cubed is 8. Plus 2/5. Square root of 4 is 2. 2 to the 5th is 32. Now our 7 isn't going to turn out quite as pretty though. So minus -14/3. 7 to the 3/2 stays an irrational number, plus 2/5 of 7 to the 5/2. So here really there's only a little bit of cleanup that we can do with this first part. So let's negative 1/12 plus 64/5 plus 14/3 times 7 to the 3/2. 7's not a perfect square, so it's not coming out. 2/5 of 7 to the 5/2. So then the only finish there is get a common denominator there, and just plug and chug. Let me just grab my calculator. And there it is. All right. Negative 1/12 plus 64/5. So negative 368/15, and then we keep the rest. 14/3 by 7 to the 3/2 plus 2/5 of 7 to the 5/2. So sometimes they turn into nice, neat, pretty integers, sometimes not. Let's see, so many of you all try one out. So maybe try integral from 0 to 1 over 2x plus 4 times dx. So in other words, this is asking for the area underneath the curve of f of x is 1 over 2x plus 4 on the closed interval 0, 1. Okay, give that one a try and unpause it when you're ready. Welcome back. So here, if you'd like, you can do a simple u substitution. U is 2x plus 4, so du is 2 times dx. We had a 1, not a 2, so we fix that by multiplying by something worth 1. So we have 1/2 integral of du over u. And you can either use your a and b. I'll do the a and b thing this time. Did the other way last time. So 1/2 natural log absolute value of u, evaluated from a to b, and then plug your x back in. So 1/2 natural log absolute value of 2x plus 4, evaluated from 0 to 1. So 1/2 natural log of 6 plus 1/2 natural log of 4. Really about the only thing that we could change in there. You can think of the 1/2 coefficient as a power, and that's a square root. Square root of 4 is 2. 6 is not a perfect square, so either this version or 1/2 natural log 6 plus natural log 2. Either of those last two versions are just fine, though. And those are, of course, in square units still. So then the last application we look at in this section is the average value over a given interval. Now, if this were just a plain constant function, average value would be simple. It would simply be the output value. But the idea is we have some curve, and we want to know the average height of that curve. Well, if we know the total area under the curve, we can then sort of think of that as being a basic rectangle. total area divided by the width would be the height. Since the area of a rectangle is base times height, length times width, width times height, whatever way you want to describe what's in front of you. So if we know the total area and we know the width, we can get the average height. So for example, if we want the average value of f of x is opposite of x squared minus 4x plus 11. And we'll go from x is -3 to x is 1. So we have you should hopefully recognize that as a parabola opening down. And we want the average height of the rectangle, or I'm sorry, of the curve on that closed interval. Well, I can find the total area underneath that curve. To find that total area, I would do integral from -3 to 1 of opposite of x squared minus 4x plus 11 times dx. So this is our total area, and we would divide by the width. Since area is width times height, if we know the area and we know the width, we can get the average height. So the average height, instead of putting it at the bottom, we'll just put it out front. So our width from -3 to +1, that's 4 units total. So we'll multiply by 1/4, equivalent to dividing by 4. So our average height, 1/4 of -1/3 x cubed minus 2x squared plus 11x from -3 to +1. So 1/4 of, plugging and chugging, 26/3 minus -42. So 1/4 of 26/3 plus 126/3 would be 1/4 of 152/3. 152 twelfths, 12 and 2/3. Now this time it is in square units. Remember, this is an average height, so this is just in regular units. That is an ugly little 3 down there. So this part was in square units, but then we divided by units. So unit squared divided by unit is just a unit. So we have an average height of 12 2/3 units over that interval. All right, so we have you all try an average value problem. So you're going to try out the average value. So same directions as last time. Find the average value. Y equals √x plus 2 on the closed interval 0, 9. Okay, go ahead and pause that. Give it a try. Welcome back. So our interval was 9 units wide. So our average height we'll need to multiply by 1/9 of our total area. X 1/2 plus 2 times dx. So our average height, 1/9 of x to the 1/2 is now x to the 3/2, which means I'll need a 2/3 as well. Antiderivative of 2 is 2x, evaluated from 0 to 9. Our average height, 1/9 of 2/3. Square root of 9 is 3. 3 cubed is 27. 2 by 9, 18. Minus a ninth of 0. Our average height, 2/27 of 27 plus 18 ninths. So that is 2 and 2 is 4 for an average height. Okay, so some problems to try out. Same for both books. I would try section 5.5, 9 to 61, every other odd, 71 and 75. If you have trouble, please get in touch with me. Otherwise, I will see you next time.